converges to the point. And he gives an example of this below. Where's this? Well, I guess the example must be in the exercises. He then defines boundary point. What's a boundary point? X in X is boundary point of S if what? X is adherent to what? I heard both S and what? And its complement, yep. So that's how we define boundary. It has to be adherent to both set and its complement. And the set of all boundary points is, of course, denoted. So we say X is an element of the boundary of X, like that, like partial symbol. And he points out that the boundary of, that was supposed to be S, not X, excuse me. And we could also, of course, write the boundary of S as being equal to the closure of S intersected with the closure of the complement of X by S. Which implies that the boundary of S is closed. The boundary is a closed set. And also that the boundary could be written as what? Here the boundary of S is the boundary of the what? Of the complement. Yep, that is correct. And finally, theorem 1.6, the closure is the disjoint union of the interior and the boundary. Right, that is true. The boundary could be defined as the complement of the closure by the interior. Yeah. Yep. All right. So like the next section is on subspaces. All right. And I probably should. That actually is a good way to generate examples. So I probably should actually state that. We have many examples already, right? I mean, every metric space we've looked at so far is an example of a space with the metric topology, right? But I would like to get to some sort of weirder examples today. This is one. If we have X is topological space, right? And if you have U, well, let's say V. V is a subset of X, all right? Then V is a topological space with topology, and here it goes. I'm going to call it tau V for the moment, all right? And what do you think we should let the topology on V be? This is either called the relative or sometimes called it's called the relative topology in this book. I often see it called the subspace topology in other books. So what you do is you just say, okay, it's going to be the collection, the family, like U intersect V, such that U is in the topology on X. This is the subspace topology, or the relative topology. The fact that any open set in a subset of Euclidean space could be written as the intersection of an open ball and the ambient space with the given subspace was presented as a theorem in the previous chapter, so that theorem has now become the motivation for making this the definition of the topology of a subspace. So with this in hand, you can do things like, I don't know, look at, say, R2 with the usual metric topology, right? Euclidean topology, let's say. And, you know, you could do things like look at the unit sphere. I mean, unit sphere, listen to me, disk, right? And then you could ask questions like, what do open sets look like in here? Well, one kind of open set would be things like, you know, I just take an open ball, right? And the intersection of the open ball here would be my U, right? And so here I'm saying that this set of all such x and y is my V, my subspace. And so this sort of partly closed, partly open, not even open, I mean, it's kind of a half, I don't know what this thing is, right? This portion of a disk, that becomes a open set for the closed disk. So the concept of what is open depends on context. This, what I just hatched in, is an open subset of the closed disk. But it is not an open subset of the plane. All right? So, now, let's spend the last 10 minutes of class looking at some weirder examples. This is and I probably should just forge ahead and follow my plan, but I decided to go off the beaten path here for a minute. This is Topology by Moncrief. This is the other contender for this course. I think this is the circulation of this edition outside the Indian subcontinent is unauthorized. Oh no, don't tell anyone. Or, no, we're in India, right? No? No. Let's see here. He's got like 70 pages on set theory in this book before you even get to any kind of fancy topologies. So, oh, come on. He's got no examples either? All right, well. Yowzers. I mean, honestly, this subspace topology generates an inordinate number of examples on its own, many of which are interesting for applications. But here's a weirder one. Everybody should see an example like this. So take a 3-point set, ABC, and he has T1 as the empty set, the whole set, the singleton containing A, the 2-point set containing AB. All right. And then he has T2 to be the empty set, the whole set, singleton containing A, double set containing B and C. He says, find the smallest topology containing T1 and T2. All right. And also the largest topology contained in T1 and T2. For what it's worth, this is section 13, problem 4 on page 81 of Moncrief's. What's that? Everything except for the singleton. So first of all, are these even topologies? I mean, is tau 1 and tau 2, are these topologies on X? Is the union of the sets inside tau 1 and tau 2 again in tau 1 and tau 2? Well, yeah, sure. If I union the last two, I get the last one in tau 1. And if I take the union of A, B, and C, I get the whole space, right? If I take the intersection, how about intersections? These close an intersection? Like this intersect that is A, this intersect that is the empty set, which is in here. Got the whole set. Yeah, I think we're okay. I think these are topologies. So what were you telling me, Sam? So what's the smallest topology containing both of these? Yeah, it seems like we could look at T small containing let me call it T containing both, for lack of a better term. So we know it has to have the empty set. We know it has to have the whole set, right? We know it has to have A. We know it has to have AB. We know it has to have BC. Why? Because those are all open sets in one or the other, right? And what else does it have to have, you said? Right, and we have to adjoin the singleton containing B because that's the intersection of these two guys, right? Yeah, I guess could we somehow get the singleton containing C from the data with an intersection or a union? Well, if this is in here, right, then the intersection of that and that's, well, that's B again. So yeah, I think that's it, right? I think that's it. That's a topology, which contains topology 1 and topology 2. So this is finer than T1 and T2. To say a topology is finer than another topology is to say that it has all of the open sets in the original topology and then some. So if you have this, if you have T as a subset of T prime, that makes T prime a more fine topology than tau, than T. And conversely, it makes T, if these are not equal, it makes that a more coarse topology. Right? A coarse topology has less open sets than a finer topology on the same set. Okay, so how about the other one? What's the largest topology contained in both tau 1 and tau 2? So you think it's just, so you think that the largest, the other one, let me call that tau tilde for lack of, I don't want to write anymore. So you're saying that the answer to the second question is phi x and then what? Just A? So that's a subset of tau 1. That's a, I mean, I say subset, I should really say subcollection. I guess it's a subset. Let me not get into that. Yeah, it's a subset. I mean, everything in here is in there, right? I mean, everything in here is both in here and in here, right? So this tau tilde, I mean, T tilde is contained in both of the given topologies. And you can't make it bigger because if you do, then if I tried to include AB, then I get into trouble with this other one and vice versa. So, yeah, like you said, it's basically the intersection. The other one's not the straight union, though, is it? I mean, I just kind of I collect these, take the things which are in one or the other, I put them together, right? Just the straight union wasn't quite enough, was it? Because I missed this. So, anyway. So that is an example. Another example. So some of the more interesting examples come once we've discussed the concept of a basis. So one of the things that gave me fits, well, there's a couple different ones that have given me much suffering in my life. There's something called the cofinite topology. There's something called the Zariski topology. There's this lower limit topology. There's a order to, there's all kinds of more. I'll try to show you a bunch of, I'll try to find more examples next time we meet as we continue to plod forth through Gamelin. If I'm behind the schedule, oh well. We're just going to keep taking it one day at a time, right, and see where we get to. But I probably have said what I need to say about the subspaces section. I should probably start in continuous functions next time. And I should probably try to cover continuous functions and a base for a topology next time. And if I do that, that should give me a natural platform to talk about the other weird examples that I haven't included yet. All right. So sorry I have not gotten to more weird examples today. I wanted to do more in that direction, so oh well. Thank you.